Okay, so when we talk about this topic called energy and chemical change, what are we, in a nutshell, what are we actually talking about? The topic it is, or the module, it is self-explanatory. We are talking about the energy. We are also talking about the chemical change. I'm saying to you, this topic, it forms part of chemistry, right? And in chemistry, what do we normally talk about when we focus on the chemistry part? We are talking about body chemical reactions and all of those things, right? So here, the energy can be studied in many different forms, and the energy can be studied in different fields. We have studied energy in physics. Now we are studying energy in chemistry. But now here in this topic, the energy that we're going to talk about, it is the energy that talks about what? It is the energy that talks about the chemical reactions. Okay? So meaning, if you have a chemical reaction, what do you need for a chemical reaction to take place? You need your reactants. And your reactants, under whatever specific conditions, will react with each other. It's either we have one reactant, or we have two reactants, or we have more than two reactants. If we have one reactant, we are talking about the decomposition. We are breaking something down. For example, if you have a big reactant, we break it down into two smaller pieces. Therefore, that's what we call decomposition reaction. But when you have two or more than two reactants reacting with one another, we can form one product or maybe two products that is called the synthetic reaction. It's like we synthesize or we compose. When you compose, we break down. When you synthesize, we build up. But you have to understand, within those reactions, there is an energy that is involved before we can form the products. Okay, so this energy that we're going to talk about, it is the energy that we find within the chemical reactions. So meaning this energy, these reactants, when they interact or interact with one another, there is an energy that is involved. And then there will be chemical change. What do I mean when I say there will be chemical change? For an example, take your eggs, right? Take your eggs and your oil. What do you form? You can form your scrambled eggs. Now, your reactants, we have the egg that has an egg yolk and albumin, or we can call the egg white. Okay, we have the yolk, which is yellow, and then we have the albumin, and then we have the oil combined together under heat. So here we're going to have heat. This is how we represent heat as as chemistry students or whatever. So this is how we represent heat, okay, with delta below the arrow here. So oil and egg combined together in the pot, we have heat, and then we have the scrambled eggs. So what happened with the chemicals? Take them as chemicals, right? Yes. So these chemicals, they're going to change. That's what we mean when you talk about the chemical change. And by the way, we know that the properties of the reactants will change, will no longer be the same as the properties of the products. For example, you can have a look at this one, the one that will make sense is this one. We have the fire, the matchsticks, we have the wood, and then what are we going to have as a product? Ash. We're going to have an ash, right? What's the color of ash? It's far different from the color of the fire, from the color of the matchsticks, from the color of the wood. It's far-fetched from that one, right? The colors are different. So we are talking about the properties. So the chemical change also leads to it leads to different chemical properties. Okay, so basically in nutshell, that's what we're gonna learn about. And we're gonna learn about some type of reactions, they give heat. Some type of reactions, they need heat. But you have to understand that there is an energy involved, meanwhile that case is happening or that case takes place. Right. So now let's talk more about the energies. Ne? This is what you need. I'm going to start with point number one when you talk about the energies. We're actually going to learn about the endothermic reaction, and we are also going to learn about the exothermic reaction. Listen, I am saying to you, reactant A and reactant B, they can both form product C. During this chemical reaction, it's either we give heat off, right? Or during this chemical reaction, it's either we introduce heat onto it's either we introduce heat onto the reactants to form the product. So the reaction can be in two different ways. That's why we need to understand that the chemical reaction in which heat energy is given out, we are talking about the exothermic reaction. Exothermic reaction is when we give heat out. Let me show you how it works. So when we talk about the exo, which simply implies exothermic reaction, when reactant A interacts with reactant B, we form C, and on this side of the reaction, we're gonna have the heat. Why do I write heat on the product side? I'm writing heat on the product side because heat, it is the byproduct of this chemical reaction. So in this case, or in this type of reaction, I don't care whether it's synthesis or whether it is decomposition. As long as I see heat as part of my product, I know I am talking about the exothermic reaction. You understand what I'm saying? And you will learn as time goes by. In chemistry, we just no longer call it, we just don't call it heat, we call it enthalpy, but you will learn that. So in this case, we are having exothermic reaction. And those in which heat is taken in, when you absorb heat, we are talking about the endothermic reaction. So endothermic reaction is a type of reaction whereby, let's say our reactant A interacts with reactant B, and there is heat involved on the reactant side, and then we form product C. In this case, then now we are talking about the endothermic reaction. Why? Because heat is being absorbed by the reactants. The reactant, they need heat. So most of the times, how are you going to be eligible to see this type of reactions? Let's talk. For an example, exothermic reaction. Where do we see exothermic reaction? The reactions that gives heat out, right? Whereby you take your reactants, you combine them together, and then when you touch, maybe the reaction is happening in a cylinder, or maybe the reaction is happening in a beaker, or the reaction is happening in a test tube. The moment when you touch that test tube, or the moment when you touch that beaker, you feel heat from the surface of the beaker. Just know that that type of reaction, it's exothermic because it is giving heat to the surroundings, or it's giving heat to the environment. But when reactant A and reactant B, you give heat and then you touch the beaker or you touch the test tube and you don't feel heat, but you see there is a chemical change. The reaction has taken place, but still when you touch the outside of the test tube, you don't feel heat. Therefore, we are talking about the endothermic reaction. So that's how we go about for these types of chemical reactions, okay? Always know there is endo and exo. The one that gives off heat, the one that absorbs or that takes heat in so that the reaction can take place, so that we can have the chemical change of the reactants to the product. That's why the topic energy and chemical change, okay? And you have to understand that heat, it is in the form of energy. By the way, heat, it is in a form of energy. Remember, energy can be anything. So heat, it is in a form of energy, meaning chemical energy converted into heat energy. That's what is basically happening. Or we're introducing heat energy, we are converting in many, you see, here, exothermic, it's chemical energy. It's gonna release heat, meaning it gives off heat energy. But here, endothermic, we need heat energy to give chemical energy. Understand? So that's what is happening here. Now, I'm gonna jump this one. Okay, I'll tell you why, but not now. This one is not that, it is important, but not that much. You will see it. It will be hard for you to understand this one, but I'll tell you how. Now, I want to jump to number 3. Now, number three, this is what we're going to do. We're going to understand the use of delta H. What do we call delta H? This delta, meaning this triangle, it means delta, right? What does delta mean? It means change, right? No, you all know this. It means change. Meaning here we are talking about H final minus H initial. But you will learn now, just right now, what is H? What does H mean? Remember, what did I say to you? I said to you, exothermic, there is heat. Endothermic heat at the beginning. This heat, it is the one that we call now H, okay? But normally we call it delta H, delta H. Now, the heat of the reaction is called enthalpy. The heat of reaction, it is called the enthalpy. So, having a look at point number 3, we need to understand the use of delta H to represent the enthalpy. It's called the enthalpy, okay? Change of exothermic and endothermic reaction, which is true. I told you with this delta, this triangle over here, it means change. Here we are talking about the exothermic reaction. We have delta H. Here we are talking about the endothermic reaction. We have the delta H. But in a nutshell, what does the delta H mean? The heat of a chemical reaction. A heat that is needed or heat that is being released. A heat that is being released is exo. A heat that is being needed, it's endo. But again, we can also call the enthalpy. Enthalpy is the same as that heat. Okay? I hope it is clear. So delta H, it means enthalpy, okay? Which is the change for exothermic. Here, change for endothermic and so forth, right? Now, let's jump to point number 4. Now, number 4, represent exo and endothermic reactions on a simple energy level diagrams. There is what we call the energy level diagrams, no? Okay, I'm not going to dwell too much on them. I'm just going to show you how does the energy level diagrams actually look like. Potential energy diagrams, basically. They kind of look like this. And there's another one that looks like this. I'll even give you hints on how to remember which one is exothermic, which one is endothermic. This one is it is exiting at bottom. This one is exiting at top. That's a trick that I normally use so that you don't get confused, but it's fine. I don't want to rush you. We'll get there. Okay. So this statement over here, number 4, learn to know how to represent exothermic. It's either this one is exo or it's endo. Even this one you will learn, just that I don't want to show you right now. Let's take time to get there. Okay. So this statement does what it means. Down, number 5. We're going to talk about, we need to understand that the breaking of bonds is endothermic, right? And that the making of bonds is exothermic. This is a very serious statement that I feel like you need to understand and you need to always remember moving forward with this topic, okay? You need to understand that when you want to break the bonds, you are doing what we call the endothermic. When you want to form the bonds, you are doing what you call the exothermic. Now it comes back to that statement that I mentioned at the beginning of this session, where I was talking about the synthetic reaction and decomposition reaction. When you compose, it's when you make or when you form, right? When you decompose, it's when you chop, you break. You're breaking something down. So, guys, you are a chemical engineer at this point in time, or you are a chemist. There's difference, by the way. You are a chemist or you are a chemical engineer at this point in time. Because, why am I saying that? When the reactants combine together, do you know that the bonds are going to be involved? So it's either these reactants, we break their bonds and they separate, right? It's either these two reactants, we break their bonds and they separate, right? Or let's reverse this. We join their bonds and it becomes one. One of the two must take place during chemical reaction. You understand what I'm saying? So if that is the case, we are also looking at endo and exothermic reaction. But always know that if you want to understand that the breaking of the bonds is endothermic, this reaction, we're breaking the bonds because we are using the heat. Where does heat goes? Heat is going to help us to break these bonds. Break the bonds. So this could be this. It does not matter how many reactants we have, even if it's one reactant, but really it does not matter because this one, the bonds are going to break off. Even for reactant A, the bonds are going to break off. And some of the parts of B will react with A. Some of the parts of A will react with B. And therefore, we have the product. But here, exothermic, we are building. So meaning, that's why we are releasing heat because we just combine these two guys together and then heat starts to get to released. Understand? So always know this. So now, here, we're going to learn on how can we interpret potential energy diagrams. I gave you I gave you a diagram on the previous slide, right? On how to actually represent those potential energy diagrams. So we're going to learn on how to interpret them. But learning on how to interpret them, then there are terms that are involved. We're going to talk about the activation energy, activated complex, the enthalpy of the reaction. We're going to learn to interpret those graphs, right? We're going to have the diagram that looks like this. I showed you on the previous session. Don't worry. I'm here. I'm going to make it simple as much as I can. We're going to have a look at diagram that looks like this. You see this one starts at low. This one, I'm going to start it at the bottom. I mean, at the top, go up. And then this part is going to end there. That's the difference between the two. I know which one is exo. I know which one is endothermic, but I'm not going to tell you. You will learn that, okay? Here, I just want to show you what we mean when you talk about the potential energy diagram. This is what you're looking at. We are talking about the potential energy diagram. And then here, you will see we talk about the heat of reaction. And then here, we are talking about the cause of reaction. You will see that. It's fine. So we're going to learn on how to interpret this type of diagrams. That's what we mean here. How can we interpret them there? And then we're going to show the potential energy of reactant particles changed to a chemical potential energy stored in bonds. You see that statement that I spoke about, number 5. We're going to interpret the statement looking at these diagrams. Okay, potential energy diagrams. And then we use these diagrams, to keep track of potential changes during chemical reactions in stages. You will see that. This is why we're going to have to interpret those potential energy diagrams. Now, let's have a look at this diagram over here. This is the cause of the reaction. We have the Cartesian plane, some sort of, right? We have the y-axis here, then there, let me put it for you. We have the y-axis, and then there we have the x-axis. Looking at this, some sort of a Cartesian plane, we can see that on the y-axis, we have the potential energy, and on the x-axis, we have the progress of reaction, or you can say the course. You can say the course or course of reaction. Okay, sometimes or some other books they use, meaning the time of the reaction, the process of the reaction. You understand what I'm saying? That's what it means. So now let's have a look at this example. We're going to take this example onto this diagram. Okay, we have two reactants. We are forming the product, which is AB. This double arrow over here, it is just an indication to show you that the reaction, it is also reversible. From the reactants to the product, from the product to back to the reactants. Now, this is what I want you to understand. We say the forward reaction is read from left to right. Yes, from left to right. That's the forward reaction because we have the double arrow over there. Ne? Compare the potential energy of the reactants to the potential energy of the products in the forward reaction. That's what you're going to do. Look, now, focus, focus. I'm not going to read here. You will read this by yourself. A plus B, it forms AB. These are the reactants. These are the reactants. Meaning here we have A plus B. And then AB is our product. Here's our product. And therefore here we have AB. On the y-axis, we are talking about the potential energy. We are talking about the energy that is involved during the chemical reaction. Ne? So now look at this. Let's compare the energy of the reactants. We are interpreting the graph now. Let's have a look at the energy of the reactants and the energy of the products. The energy of the reactants, I said this is some sort of a Cartesian plane. Obvious, here we have what? Here we have 0 is to 0, right? So the energy here, the origin is 0. But look at the energy of the product at this point. So which between the reactants and the products, which one has the higher energy according to this diagram, according to the shape of this diagram over here? We can see that the energy of the reactants or the potential energy of the reactants, it is much higher than the potential energy of the products in this case. We have high energy of the reactants. We have lower energy of the products. We are comparing them. This is lower than that. This is higher than that. So what does that mean? When we have high energy of the reactants, low energy of the products, we say energy must have been released during the reactions. So that means you see the shape of this graph whereby the reactor, guys, this statement is very important because when we solve the question papers, they're gonna ask you choose higher or lower than, and then give a reason. Why do you say that? This is the reason that you're gonna give because the energy has been released during the chemical reaction. So listen, when the energy of the potential energy of the reactants is higher than the potential energy of the products, just know that we are talking about the exothermic reaction. How do we see it's an exothermic reaction? Because energy must have been released during chemical reaction. Okay. There is a trick that I use. They can do this. You see this shape of this graph. They can ask you, is this exothermic or endothermic reaction? Without giving these reasons, I'm going to say it's exothermic. Why am I saying that? This is a trick that I can give to you. You see here, we start at the bottom, we exit at the, we start at the top, we exit at the bottom. Exit, here we are, you see it's like exit at the bottom. So this exit at the bottom, I call it exothermic reaction because it is exiting at the bottom. That's the only way. If you know there is exit at the bottom, therefore you have exothermic. If it doesn't look like this, then it's endothermic. Simple as that. When I was in high school, I would confuse these graphs. I would confuse which one is exo, which one is endo. So I had to make up this in my head to know that I start at the top, I exit at the bottom. This is exiting at the bottom. Therefore, it is exo. Because exo exit at the bottom. I take it like that. You understand? Because sometimes you'll get confused. But always know that if it is the case, now you can look at this. We have high reactants. We have high energy of the reactants than the energy of the products, potential energy of the products. That means energy has been released. If you know this is exo, you will know that energy is released. So sometimes I get confused, man. Man, how to come up with all of this information over here? You know what I do? Let me show you. I do this. I draw this and then, okay, now I can interpret this. I see here, this is higher than this one. This is, and I know all the time here it's reactants, here it's products, here it's reactants, here it's product. So all the times, here's reactants, here's product. And then the energy of the reactant is high. The energy of the product is low, obvious. If here it's one, then there it's two, because that's above, like, come on, this is a Cartesian plane. You understand what I'm saying? So I can see, oh, here I have high potential energy of the reactants compared to the product. And again, it is exiting at the bottom. It's exothermic. So since well, it is exothermic, that means energy must have been released because it's exothermic. Energy must have been released during this chemical reaction. So that's what is actually happening, okay? So basically this slide here, we are looking at exothermic potential energy diagram. What do we know about the exothermic potential diagram? We are interpreting this, right? The potential energy of the reactants is higher than the all is higher than the potential energy of the products. Okay, that's what is basically happening over here. Now let's further, let me see. Okay, it's fine. Let's further interpret this diagram. Forget about these blue colors and all that. So I said there are terms that are involved in these diagrams. Like we're still looking at the very same diagram over here. There are many terms that are involved, such as this term, potential energy of activated complex. We're going to look at this term, which is called activation of forward reaction activation with catalyst. We're going to talk about the catalyst. And sometimes they're going to give you this diagram and they're going to ask you to label all of these things. Now, let's start with A. A, it is called potential energy of activated complex. This point over here, this peak, look at the red graph, which is the same as this graph, which I'm talking about this peak over here. It's A. It's called point A. Let's go back to this diagram. So I'm talking about this peak over here. This peak over here, it's called, it's A. It's called activated complex. You can just call it activated complex, you see, like here, or you can call it potentials. Don't be confused or surprised when tomorrow they say it's potential, because this is potential energy. Maximum of it is a maximum point of this graph over here. So what does activated complex mean to us? It is the intermediate molecule that forms when reactants have an effective collusion. It is unstable and temporary. Listen, this is a chemical reaction, right? So now, this is like quite microscopic, and you need to understand it. We have the reactants. These are the particles of the reactants. Let's assume that these are the particles of the reactants, and now we have the products. When this interact with that, and this interact with this, these are the reactants, right? They interact with one another. They start with this energy, right? Potential energy is here. And then they come close to one another, right? When they come close to one another, the energy, potential energy increases. The potential energy increases because they want to interact with one another. Like, they want to combine together. But you have to understand that when you talk about the atomic model, we know that the atom has the protons and the neutrons in the center, and they have the electrons. So when this atom interact with this atom, you see these electrons, they are the same charges. They're gonna repel each other. But because we have the protons at the center, these protons also, they're gonna repel each other. But at the end of the day, they want to combine to make one thing. So that's why we need more energy to combine these things. Hence why here potential energy shoot rapidly up, because we need more. We need extreme energies. We need high energies to combine these two guys together. You understand? So that's why these reactants, they start with this energy, and then we try to combine them. Then more energy is needed, and then it reaches activated complex. When it reaches activated complex, that's where the products are about to be formed, because here we have the reactants. You see this half over here is for the reactants, and this half over there is for the products. So that's why we say activated complex, it is the intermediate meaning it is the middle. It is the intermediate molecule. You see these molecules, intermediate molecule that forms when the reactants have an effective collision. It is unstable and it is temporary because it can fall anytime. So this activated complex, it's when these molecules are now at that level to say now they can form the product. Like everything is perfect now. And therefore, immediately when they reach activated complex, energy drops fast. And then we get the products of what we are actually looking for. So you see this portion over here till here. It is temporary, this thing. It happens fast and it needs more energy, and energy starts to drop. And then now we form the products over there. You get it? So the activated complex, it is that maximum peak where now the reaction is about to happen. For your exam purposes, learn to know how to define an activated complex. I was just explaining to you what does activated complex talks about, so that when you read this definition, it doesn't sound difficult to understand. Okay, so make sure that you know these definitions. All of these definitions for CAPS purposes. Okay. If you need clarity, feel free to ask. Now let's look at number B. You see number B, it is this blue arrow over here. Number B, it is this. You see where the reactants end. And then you see this line from the activated complex to this line. It's number B, ne? Right. So what does number B mean? It means activation energy of the forward direction. Activation. When something is activated, what does that mean? It is stimulated, right? Now it can work. So when you talk about the activation energy, this is the most thing that you're supposed to always remember in your head. We are talking about the minimum energy or minimum amount of energy needed for the minimum energy that is needed for the reaction to take place. It is that minimum energy. Here's the thing. For the reactants to interact with one another to form the product, we need energy. We need a spark that says, aha, these two guys, they combine together and they're going to form a product. Because honestly speaking, these things, they won't just stand there and say, let's combine together to form a product. Just like a male and a female, right? There must be energy between them. That energy is called chemistry. You guys are familiar with these things. There is a chemistry between these two guys. And when there is a chemistry between these two guys, they start to combine and they do reproduction and they have a product, which is a baby. You understand? So that means that energy that is needed for a reaction to take place. Without that energy, the reaction won't really take place at all. So here in chemistry, that energy that is needed, that minimum, we don't need much of it. We just need that spark, you understand, between two people. So it is called the minimum amount of energy needed to start the reaction in the forward direction. What is the term for this blue graph B? It is called the activation energy. Tomorrow when they say to you, define activation energy, normally they don't use activation energy of the forward. It is just activation energy. You understand? You don't have to include forward direction when you're defining activation energy. You can say activation energy, it is the minimum amount of energy needed to start the reaction. That's it. But if they can say activation energy of forward reaction, therefore you will say in the forward direction, then you will include this in the forward direction if it is needed in this way. Okay, so that's how we define activation energy. So that's number B. So let me go for another session.